All right, so one thing that's true is that differentiability implies continuity. So if a function is differentiable at a given point A, then that means it must be continuous at that point as well, okay? So it has to be continuous in order for it to be differentiable. All right, and then, these are kind of three topics that we've talked about now to this point. We talked about the limit, continuity, and now differentiability. And so the limit has the lowest burden of scrutiny, right? Like the limit could exist even if it's not continuous, right? We could have from either side the function approaching that point, but at that point the function doesn't exist, or at that point the function is undefined, right? So the limit is kind of the lowest standard, and then for it to be continuous, remember you have to be able to trace your pencil along it the whole way, and so not only does the limit have to exist, but the limit at the value at that point has to equal the limit, right, for it to be continuous. So f of a has to equal the limit as x approaches a at that point. All right, and then differentiability, not only does it have to be continuous and the limit exists, but there are other things. You can't, for it to be differentiable, you can't have any breaks, like, or and that implies continuity. So let's use some of the more subtle things. So you can't have any points. Okay, so for example, absolute value function, this is not differentiable at the peak or the valley there, right, at the point. Okay, and so it has to be a smooth curve. So for it to be differentiable, it has to be smooth. So it can't have any points. It has to be kind of a smooth curve, or it could be a line too, but it just has to be smooth. It can't have like a sharp peak like that. The other thing is you can't have any undefined areas where undefined slope. So like if you have a function that kind of at some point has a vertical a change towards where it's vertical, and I'll show you one in a second instead of me trying to draw it, but that would give you a situation where the derivative doesn't exist. And then the last one is oscillating. So you could have a place where it's oscillating, where it's going up and down at that point, and even if it's continuous, it may not be differentiable. Okay. All right. So if it's differentiable, it implies these other things, right? So if it's differentiable, it has to be continuous, and the limit has to exist. All right. But if it's continuous, that doesn't necessarily mean it's differentiable, right? Like here, this is a continuous function, but it's not differentiable. Like if I were to, use our definition formula or things like that, I wouldn't be able to, I wouldn't get the same thing from the left side as I would from the right as I got closer and closer to zero. And that's because this is a constant function, right? This is constantly negative on this side and constantly positive on this side. So the limit from the left is not going to equal the limit to the right, even though, and here, like, the slope isn't exactly zero because it's a point, right? So it's not like a level value where the slope would be horizontal, the tangent line would be horizontal. Here, this is actually a point, which is a little bit different. Okay, so when you have a point that's not differentiable, another thing that's not differentiable, this is what I mentioned before, is when you have a situation where the function at some point has a vertical slope, like or a tangent line that's vertical, a vertical tangent. That's when the derivative won't exist at that point, right? Because like the derivative is the slope at that point. And what's the slope of a vertical line? The slope is undefined, right? So if you have a vertical tangent, that means the slope m10 would be undefined at those points, right? And so the derivative won't exist. It won't be differentiable at zero here, okay? So it would be differentiable everywhere else, but just not at zero, okay? Same thing with that previous one. It would be differentiable everywhere but here, right? Okay, and then last, we've seen this function a few times, but here's an oscillating one, and this function by itself, or this function by itself, is oscillating, and it has a discontinuity. But here we're plugging in a value, kind of plugging up that hole, but still it's not differentiable, because think about as we're zooming in there and we're trying to find the slope. The slope is going up and down, up and down, up and down, up and down, right? And so from either side it's going up and down, and so the limit, the definition of our derivative is a limit, and it doesn't converge, right? The limit does not exist, and so therefore it's not differentiable, even though it's continuous in this case. So here's a good bonus question. We're not going to do these. These will be either challenge or bonus questions on a test. But if I ask you for a piecewise function to be continuous and differentiable, for it to be continuous, we've seen that before, right? We just know that if we plug in -10 to this function, the output has to be the same as if we plug in -10 to this function, right? And that means they'll meet up, right? That one side will equal up the other side. But for it to be differentiable, not only does that have to be continuous, not only does that have to be true, and you have to check for that to see that they're the same at those points, but you also have to see is the slope the same at those points, right? So you'll have to do the definition of the derivative here and find basically. So what you'll have to do is you have to see, like, let's call this function, let's call this g of x and h of x. So for it to be continuous, g of -10 has to equal h of -10, right? So that's what you have to check for it to be continuous. For it to be differentiable, that means that g primed of -10 has to equal h primed at -10, right? The values of the derivative have to be the same at those points. And so that's what you would check for, is you'd find, the derivative of this, the derivative of this, plug in 10 and see what you get. And then in this case, you'd solve for B and C. All right. So I just wanted to show you that. We didn't do that whole example, but that's kind of a good idea of a bonus question. Here is the same thing. But I like on this one, they have the diagram, and it says, you want to create a track. And so if it's continuous and differentiable, that means that it'll be a smooth ride for that little car here.